All right, let's begin. Welcome, everyone. Thanks for coming. This is Extending Kubernetes with Storage Transformers. My name is Andrew Lytvynov, and I'm a software engineer on the Google Kubernetes Engine security team. So today, I'm going to explain to you briefly what transformers are, why they exist in Kubernetes. And then most of the session will spend actually walking through the guide of how to implement one. So starting from a base transformer built into kube-apiserver, then to envelope transformers that help us with key rotation and management, and then into KMS plugins. And lastly, I want to talk a little bit about how we secure KMS plugins that we end up at the end with. So to understand what storage transformers are, you want to look at kube-apiserver as consisting of two layers. You have the RPC layer, where your requests come in and out, handles authentication, authorization, parsing, validation, all those things. And then there's the storage layer, which is essentially a kube-apiserver talking to etcd and doing any serialization and deserialization. At the RPC layer, Kubernetes provides you with extensibility in the form of webhooks. So you may have heard about admission webhooks. The idea is pretty simple. You just provide some custom piece of logic that is injected in the path of all of the objects to traverse the API. The same thing at the storage layer is provided by transformers. So KMS plugin is an example of a transformer, but the idea is the same. You inject some custom logic that sits in between your objects as they can come in and out of etcd. By convention, transformers look at all the data as opaque byte blobs, while webhooks look at them as actual parsed objects. So they will look at individual fields and maybe change their behavior, maybe mutate the fields based on some logic. Obviously, that's just a convention. Transformers are free to parse all the objects as they come in and out. But if you find yourself needing to do that, webhooks are probably a better fit for your use case. So why talk about transformers at all at KubeCon? First of all, transformers are somewhat under-documented. It's kind of difficult to figure out how the code base is structured, how to implement one. And my colleague, Alex Cherniakovsky, has spent a lot of time working with transformers for GKE. And there's some valuable lessons to be learned from his work. And finally, with this whole new shared knowledge, I want to encourage some new contributions, maybe to just improve the code base, maybe to redesign the entire feature, maybe to implement some new kinds of transformers for use cases that are not obvious right now. The reason transformers were created in the first place in Kubernetes is because by default, kube-apiserver does not encrypt any of your secrets at rest. So that means all of your data that you submit to your API is stored in your etcd data file, encoded in some binary format, but essentially plain text. Transformers exist to solve that for at least the secrets by encrypting them before storing to etcd. The reason it's a problem is if you look at someone, for example, creating a new secret in your API, they send it to kube-apiserver. Then kube-apiserver encodes that in some format, but essentially stores it in plain text. So if an attacker gets a hold of your etcd data, they have access to all your secrets, anything that your workloads running in your cluster have access to. You might think, well, you spend a lot of time hardening your master VMs, your databases, your API, you have all the RBAC rules, everything is bulletproof. But consider this case for offline attacks. We have a cluster here where we have a credential stored in our etcd that is just a credential to authenticate to some remote database that stores a bunch of sensitive data. Our attacker comes along, tries to muck around with our VM or API, and nothing works. It's indeed like a really hardened setup, a very well protected cluster. But we also configured our cluster to do a daily offline backup of etcd data for disaster recovery. And the backup server where this backup ends up happens to be not as well hardened as your master VM. So if an attacker gets access to that, they can use the credential to access the data store, and basically it's game over. And notice that the attacker didn't have to compromise your API, your cluster VMs, your database, nothing. They still got the access to sensitive data just because one of these backup servers happened to be not well hardened. So the point here is that there's many vectors to accessing and exfiltrating etcd data that may not be obvious right away. So you might think that, okay, someone got the dump of this huge database of etcd, there's a bunch of objects, and it's really, really hard probably to parse everything out, figure out which objects are secrets or not, figure out what the format is that Kubernetes stores the data in. But let me show you this. So I'm going to run a little helper that will do the typing for me, but it's all running live. So I have this etcd data directory dumped from a running cluster. After a quick search in the documentation, I know that member-snapdb is where the data is actually stored. So I'm going to run the strings utility on this file, and strings utility is essentially available on any Linux distribution, pretty much built in, and it will print out any data in the file provided that's textual. So anything that's binary is discarded. Anything that looks like a piece of text will print out. So here, like if you scroll around, you can see there's some object URL looking things. There's some full objects in JSON. So that looks promising. I'm just going to grab this output for a string secret and immediately find one finding. It's called devdb secret 01. Okay. So I'm going to pass the -c flag to grep, which will just show me the lines around where this match was found. And here at the end, you can see that we have our secret name, namespace name, and the contents of the secret in plain text. So what I'm trying to point out is that this is all the tooling I needed to extract secrets in plain text out of my etcd data dump. That's applicable to any standard Kubernetes installation that doesn't do encryption at rest. All right, so hopefully I kind of convinced you that encrypting secrets at rest is a useful thing to do. Now let's jump into the main section and how do you actually implement one? How do you create it if you have a new idea for a transformer? So this URL here, I have a fork of Kubernetes where I built a transformer that's following exactly the same steps I'm going to show you right now. The steps I'm going to be showing in the slides are more abstract. I'll just use some code snippets for demonstration purposes. But on this fork, I implemented a transformer that does SM4 encryption at rest alongside all the other available transformers. And if you're not familiar, SM4 is an encryption algorithm similar to AES that's been designed and approved by the Chinese scientific community. Before we jump into the steps, at the bottom right of each slide will be the exact commit on that fork that implements this step. And I'll also try, these are actual links to the directories and files where the changes I'm going to talk about are need to be made. So first step, obviously, we need to implement the actual core of our transformer, what it does. And that's done by implementing this transformer interface. This is a pretty simple interface, just two methods. You get some data before or right after it's being read from, right after being read from etcd, and you have to transform it back, and same thing in the opposite direction. So that's specific to what your transformer does, but should be pretty straightforward. Next step, transformers don't really exist in isolation. Usually they need some input. So for encryption transformers, there'll be encryption keys. There might be some other data you might need to provide. All this configuration is passed to kube-apiserver through a YAML file at startup. This file contains an encryption configuration object. And essentially it lists the types of resources that the transformer applies to and the specific transformers. So providers is just a synonym for transformers here. And here I sort of sketched out what I want my transformer to look like. It has a key and a field of some other type as input. So now I convert that last chunk into a Go struct, into which I'm going to parse out the YAML. It should basically mirror the exact YAML object that you expect to get. And you might notice there are two links to the files here. And yes, you need to implement the exact same struct in two places. You might also notice that we're using JSON tags in our struct fields while we are parsing out YAML. But we don't have time to make our code base make sense. We just have transformers to write. So let's go next. Step 3, you have your configuration. Now you need to register it as a possible transformer in the encryption configuration YAML I showed before. And to do that, you just add it to an existing struct at the end. So here I just added as the last field in the same two files. It's pretty straightforward. Next, I need to explain what prefix transformers are. Prefix transformers exist for the purpose of not having any conflicts between multiple transformers. So when a prefix transformer writes some data to etcd, it prepends this static prefix that's highlighted here. to the data. And then when it reads it back, it actually checks the prefix, strips it. But if the prefix does not match, you know that there's some misconfiguration, there's something wrong. And instead of returning corrupt data, it will throw an error. So here, yeah, I just grabbed another etcd data file, and the prefix looks roughly like this. You don't need to implement any of that yourself. Prefix Transformer is already implemented. You just need to instantiate it and give it a prefix and your actual transformer. You register your prefix in this const block in the linked file. And the const block is at the top and lists prefixes for all the other transformers that already exist in Kubernetes. It's pretty simple. So last step, we have our configuration struct with all the inputs for our transformer. We have our transformer implementation. Now we just need to instantiate that implementation from the config. In the linked file, you create a new function that takes your configuration as input, takes your prefix as input. That will be a good place to validate the configuration. So if you have any keys you need to parse, if you have any other configs that need to be validated, that's a place to do it. Then you instantiate your transformer implementation from this config. And right before returning, you wrap it with the prefix transformer, so it handles all this prefix thing for you. So great. Let me show you how that looks in practice. So here in this other tab, I'm going to start my local cluster that is built. So it just uses a modified kube-apiserver binary that was built from my fork. Here I have my encryption configuration that I passed to that cluster. You can see this SM4 transformer config field here, and I just give it a single key, the encryption key. So start the cluster in a separate tab, and I'm going to make sure that it's actually running, so it's running on my local host live. I'm going to create a secret. I'm going to give it 2 fields, username and password, and I'm going to name it devdb secret 01. So I'm just going to, this is how it looks like in YAML when you print it out as a client. You will notice that these fields don't look like the actual fields I set, but these are just base 64 encoded. So this base 64 decoded is just password 0. And this is this is working as intended because we're not doing encryption at the application, at the client layer. So not at the API layer, we're doing it at the storage layer. So client should have no difference in experience. Now for comparison, from the previous demo, this is the command we ran, and this is the output we got. So we got our username and password in plain text here. Now the same command ran against this new cluster. We see that we still find the secret identifier, but then we have our prefix that I used for my transformer, and a bunch of binary data that's not printable, and that's the encrypted data. So, okay, great, that works, but we have 2 problems. The first problem is that we provide this encryption key at startup via the YAML file. So that means if you want to rotate the key, you need to restart kube-apiserver, you need to update this encryption configuration. It's a lot of manual work, and it's a little bit of API downtime, so that's not great. But the bigger problem is that our key is stored in plain text on disk. So the encryption configuration YAML is passed to kube-apiserver at startup as a file path. And odds are that that file is stored on exactly the same disk where you store your etcd data. So if the attacker compromises the entire disk, not just the directory, then they have all the keys they need to decrypt all the secrets. To help us with those 2 problems, we're going to use envelope encryption and envelope transformers. So it's a bit of a tricky concept. I'm going to walk it step by step, so bear with me. The idea behind envelope transformation is that you use 2 keys instead of 1 to encrypt every piece of data. So you have your data encryption key, or DEC, which is used to encrypt the actual piece of data. And then you have your key encryption key, or KEC, which is used to encrypt the DEC. When you actually store the data, you encrypt it with the DEC, you encrypt the DEC with the KEC, you concatenate those 2 parts, and that's called the envelope. That's what you actually put into etcd, while key encryption key lives outside of the master VM, completely on a separate machine, a separate infrastructure. Key management services, or KMSs, are a good fit for handling KECs. That's their whole idea, is that they store your plain text keys in some secure infrastructure and only expose the operations that those keys can perform, like encrypt, decrypt, sign, and so on. So the idea here is that we use KMS or something similar to host the KECs, and never let them land in plain text on our master VM. So master only has these like encrypted blobs in the envelope. So that solves our second problem of keys being in plain text. The first one of key rotation and management, I'm just going to walk by example so it's a little clearer. So we have our KMS provider with the CAC, and most KMS providers allow you to automate key rotation. So here we have configured it to create a new version of the CAC every month. When you write your first secret, it gets its own deck, deck 1, and then that deck 1 is encrypted with CAC 1. If you create another secret, you get a separate dedicated deck for every single secret, and then that deck is encrypted with CAC 1 again. Now, some time passes, our automation kicks in, it creates a second version of the CAC. Some more time passes, it gets another version. Now, at this point, if you create a new secret, it will get its own deck as before, deck 3, but this deck will be encrypted with the latest version of the CAC, so CAC v3. If you update an existing secret, it will notice that the CAC used was an old one, and it will create a brand new deck for it, and then encrypt that deck with the latest CAC, CAC v3. So that's how you can gradually roll and update all of your secrets to use the latest version of the CAC without having to do any manual rotation, any restarts. You can also manually trigger a secret update to sort of indirectly update to the latest CAC so you can clean up some older versions. So that sounds like it solves our problem, but it's pretty complicated. There's a lot of keys flying around, a lot of encoding and creating envelopes and whatnot. Well, luckily, you don't need to do any of that yourself. That's already implemented for the most part in Kubernetes. There's this envelope transformer type that takes two pluggable pieces of functionality. It has the envelope service and the base transformer func. So the base transformer func is what's actually used to encrypt the data with a deck. Envelope transformer would create the deck for you, and then it will call this function with the deck so you can return the initialized transformer from it. So you can reuse the same transformer from step 1. The other part is the envelope service, and that's actually an interface. It has just two methods, and it's used to encrypt the deck with a CAC. So the idea is that the service is some sort of a remote service that doesn't expose the CAC to you in plain text. So we could potentially implement the service interface for a lot of possible KMS providers like Vault or Amazon Key Service, but following the Kubernetes philosophy, we don't actually want to put any third-party, any vendor code into the upstream Kubernetes repository. Instead, we want to provide a standardized extension point and sort of hide this third-party code outside of the tree somewhere. For that, there exist KMS plugins. The idea behind KMS plugins is that they are lightweight proxies, local proxies on the master, that expose a standardized interface that kube-apiserver knows how to talk to. And then they proxy those requests to the KMS provider using whatever protocol that provider happens to be using. They are already built into Kubernetes. You can specify them in the encryption configuration. You just have to give it a name and a Unix domain socket to talk to. And Unix domain socket is an actual explicit limitation. You cannot have a remote KMS plugin. The reason for that is this basically eliminates a problem of needing to authenticate from kube-apiserver to the KMS plugin. And usually there's no reason to have a remote KMS plugin anyway. This Unix endpoint should serve a gRPC service that implements this definition. It's basically the same as the interface we looked at a few slides back, but with an extra version method for just some metadata. Just to visualize it all together, how the entire flow works with the KMS plugin. Say your user, your operator submits a new secret, pushes it to the API. kube-apiserver then generates a new deck. It encrypts the data with a deck. Then it calls the encrypt RPC towards the KMS plugin with a plain text deck. That gets proxied over to the KMS provider using that specific API. KMS provider encrypts the deck with the CAC, returns back the encrypted blob that gets returned back to the kube-apiserver. kube-apiserver appends the encrypted data in an encrypted deck and stores that envelope in etcd. So nothing unencrypted ever touches the disk, and deck only exists in the memory of kube-apiserver. Okay, two other steps that are optional. By default, KMS plugin will use AES encryption for DEX. So if I'm encrypting data with a DEC, if you want something else, and in this case I wanted my DEC to be an SM4 key, you need to do a little bit extra plumbing. So here I added a DEC type field to the existing KMS configuration, and that's the YAML configuration blob that's being parsed. And then I added a switch to the function that initializes KMS plugin, where based on the type, I will replace the function that initializes the transformer, so I can reuse the same transformer from the first step. Lastly, most likely you don't need to implement your own KMS plugin. There's plenty of officially supported plugins from a bunch of providers out there. Here's just a small selection of them. So if you search around, you can probably find one and just use it. But if not, it's pretty easy to implement. Okay, now you should roughly understand how the whole code base is structured on transformers, how to implement one. The last thing I want to mention is threat model for KMS plugins, or basically how to help secure the KMS plugin. So the problem here is that KMS plugin talks to a remote KMS service, so it needs to authenticate somehow. It needs to provide some credential. In this case, let's say it uses a static token that's passed with a request for authentication. We also have our cluster configured to do a full disk backup of the master for disaster recovery instead of just an etcd database. So it might be easy to overlook and just store the token on disk in plain text for KMS plugin to read and use. But if our attacker compromises the offline disk backup, they essentially own everything they need to decrypt the data, and as long as they can figure out this whole envelope and decryption dance, they can get access to your secrets. So our goal must be to not ever let the plain text token touch the disk. And to do that, one approach I want to propose is using Trusted Platform Modules, or TPMs. If you're not familiar with TPMs, they are little crypto coprocessors. They're usually built into all of the server motherboards as an onboard chip. There are also virtual versions of them, so you can create a virtual TPM for every VM running on a server. And the main idea behind them is that they have a little region of protected memory. And that memory is completely isolated from the host. So if you have full root privileges on the machine, or if you have compromised the kernel, you can still not read that memory. And you can only interact with it indirectly through commands that manipulate it, but you can get it in plain text. And also, TPMs are bound to the specific host they're on, so you cannot just like move it over to a different server or copy it over. You have to be physically on the server where this TPM exists to access anything that's inside of it. Okay, so first idea might be to just put the token in a TPM because it's protected memory, right? But we actually need to read the token in plain text in order to be able to pass it to the KMS provider. So we cannot put it directly in a TPM, but what we can do is we can use a encryption key stored in the TPM and encrypt the token with it before storing it on disk. And this is called sealing. And basically, in order to unseal the token, you need to be physically on the master VM having access to the actual TPM to get access to this key and decrypt it. You might think, why don't we just like skip this whole thing and use TPM as a KMS? The problem is that TPMs are really low-powered devices. They have very limited memory, so you can only store a handful of keys there, and at least physical TPMs will be really slow in encryption and decryption, so they'll really slow down your API. So they're not a good fit for like in being something in request path. So yeah, having this token sealed should help us protect against compromises of offline backups. In summary, transformers are a way for you to add some pluggable custom logic in the path of data that's being stored into etcd. And there's multiple layers of transformers that sort of were built historically. There's the standard transformer that just does the thing to data. Then there's envelope transformers that use multiple keys to encrypt the data and help from exfiltration of the root key. And then there are KMS plugins that are just a type of envelope transformer that talk to a KMS provider for hosting KEX. And finally, TPMs are one possible option for protecting the credentials that KMS plugins might use. Now, I want to encourage anyone to strongly consider encrypting your secrets at rest if you're not doing it already. Hopefully, there's enough evidence that this is a problem worth addressing. And also, I encourage the audience with the new information about transformers to actually go out and contribute to the transformer code base, maybe propose design changes, maybe implement new types of transformers that don't only do secrets encryption, and maybe implement a KMS plugin for a provider that doesn't have one already. Finally, here's a few links to the previous talks on the KMS plugins and TPMs from previous KubeCons that might be interesting if you actually want to dive into this deeper and implement your own transformers. Right, thank you very much. And if there's any questions, I believe we have a few minutes. There's a microphone behind you.
I'm wondering why this kind of functionality is not implemented in GCT.
In where?
Is not implemented in ETCD.
GCT?
ETCD. The boundary you have.
Sorry?
The boundary you have is between Kubernetes and ETCD, right? ETCD.
Oh, etcd?
Yeah.
Why is it not implemented on etcd layer, you mean?
On the below, on ETCD instead. On the lower layer.
I'm sorry.
The storage layer, I mean.
Why does etcd does not do that by itself,
Yeah,
right?
yeah.
So, so there's also something called like file system layer encryption or disk encryption, and that usually is done by most cloud providers already. The problem, so those two things are not achieving the same goals necessarily. They are supplemental. So both are needed. The thing that full disk encryption provides you is protection against someone physically running and like stealing your hard drive, like someone running into the data center and grabbing the hard drive and then mounting and reading data. As long as that hard drive can be put online in a data center and decrypted at runtime, which usually happens with backups, you don't even see that the disk was encrypted in the first place. You usually see the data that's like at a higher level that was already decrypted and provided for you. So full disk encryption is a supplemental feature. Now, etcd could, in theory, implement encryption of its own. Just say, like, everything that's written to etcd is being encrypted before it touches the disk. That could be done. I've not been in touch with etcd folks about it, but I assume it has exactly the same problems, is that you have to specify or provide some key coming from somewhere to do the encryption. Usually the problem with the encryption at rest is not the actual fact of encryption, but it's the key management that's associated with it. And theoretically, etcd could implement something similar, but they would have the same exact problems facing them. Another reason is that encrypting everything might affect performance. So if you have encryption that's based on some remote service, not the local key, then all of your objects that are being read or written will incur this penalty of some remote call. And that most likely is a big penalty. All right. Cool. No more questions. Thank you so much.